It's okay, right? Yeah, it's
okay.
on. Yeah.
Okay. So can you put it on standby for now? Fine. So today we're going to continue a discussion on the honest covariant computation of the string S matrix. In particular, we'll more carefully than last time write down the path table that we're interested in, work out Hardy-Pope, of course, in more detail, and then by the end of this class also begin to study a symmetry of this action, namely PLS symmetry. Okay, so let me quickly remind you what we started talking about last class. Let me remind you that what we started talking about was that our limited goal at the moment was to calculate string S matrix elements. Okay, so the string S matrix elements, at least intuitively, is related to amplitudes involving long tubes going off to infinity somewhere in space-time, and going off to infinity in a particular way. That is, the vibration on this tube, once you go far enough, and each of these tubes settles down to a particular state of string theory, a particular state of the system. Okay. Now, inside there you can have as many holes as you wanted. Okay. The number of holes would be related to the loop order of the relevant process, and in terms of usual computation. And then we use the state operator map to replace each of these long tubes by an operator insertion. Which operator? Well, the operator corresponding to the state by the state operator. Okay? So our final goal in the end was to take some compact Riemann surface. Okay. The simplest would be a sphere, but we leave it. There could be some holes here, it could be a torus, so two-handled. Okay? And we compute correlation functions of operators. This is our goal at present. It may turn out that we'll be able to do more. Calculate the equivalent of off-shell amplitudes. If so, we get lucky. It will turn out that basically we aren't able to do more. But at the moment, this is all we're trying to do. And we'll see why it becomes more difficult to do more as we understand the answers. Okay, great. So our goal was then to write down a path integral that did the computation. Yeah. So let's try to be systematic. So let's say that the number of insertions of operators, let's call it capital I. So I operator insertions. So we can be calculating an I point function, a scattering process involving I particles. Okay? And we had decided that on whatever genus surface we're working, we will choose some fiducial metric, some class of fiducial metrics which have the property that via a diffeomorphism plus Weyl transformation, any metric on that topology can be related to one of the metrics in this class of metrics, via this transformation. Okay? The class of metrics we were dealing with were labeled by some number of real parameters. These parameters we call Ti. Okay? And they have a name, they call moduli. Okay? And let's say that I is equal to 1 up to 2n. We'll turn out that, as we'll see as we go on, the number of these moduli is always even. So that's a complex moduli. Okay. We also were worried about the fact that just asking that our metric, it could be that there are some Weyl plus diffeomorphism transformations that annihilate the standard form of the metric. Okay? Leave the standard form of the metric intact. For instance, on the plane, if we're really interested in the plane, all conformal transformations, which are combinations of Weyl plus diffeomorphism, Weyl transformations and diffeomorphisms, leave the flat metric on the plane intact. Okay? So, I assure you that while the number of conformal transformations is infinite, we will always be interested in compact Riemann surfaces. Okay? Most conformal transformations blow up in infinity. So if you compactify the plane, most of these conformal transformations will not be allowed with singular transformations, and understand all of this as we go on. But the one point about this that I wanted to show you about, as we'll see in detail as we go on, is that the number of these wild plus diffeomorphism transformations that are unfixed by requiring that we stick to a particular that the metric takes a particular form is always finite, and so let this number be 2j. Let the number be 2c. Number of unfixed. Okay, since we've got this will always turn out to be yeah, that's right, 2. So since we've got 2c unfixed wild and diffeomorphisms, just requiring the metric to be of a particular form has not completely fixed the issue. So what we decided was that we will, in addition, take the positions of c of the insertions, c of the operator insertions. Okay, so we will assume that m is greater than c, greater than equal to c. Okay, as we will see, it will turn out that anything with m less than that violates this inequality doesn't calculate anything physical. So the assumption will not be a physical restriction. Okay. Now, since each operator insertion is an insertion at 2 points, because we're dealing with a 2-dimensional surface. Okay. If we fix the positions of m operators to be at c specific locations of the 2-plane, to be at c operators to be at specific locations of the 2-plane, we fixed an additional 2c diffeomorphisms. Okay, so what we do is use the unfixed diffeomorphisms plus y transformations, to put the positions of c different operators at specific points on the worksheet. Okay, so we choose these. Choose the points of insertion to be sigma 1 0, sigma 2 0, sigma c 0. Some given points, which could be anything you wanted. 2c is the number of unfixed, but each operator has a position in a 2-dimensional space. So the sigma is a 2-dimensional set of coordinates. Okay, so these are the coordinates that we will fix everything. Okay, so this was our basic set. So then, what did we want to calculate? What we wanted to calculate was, the initial thing we started out wanting to calculate was path integral over all matrix, path integral over all the fields of a field theory, which is just the x mu's. Okay, then exponential of minus the Polyakov action. Okay. And then anything associated with operator insertions. And you remember that these operator insertions we would always choose to be integrated over the worksheet. Because what we wanted to do was to fix that cubes in space-time went to some specific points, but not that they started off at some particular point in some particular worldsheet parametrization. I mean, clearly that would be something that broke diffeomorphism invariance. It's nothing worldsheet diffeomorphism. There's nothing special about particular points on the worksheet. Okay, so the insertions are d2 sigma, let's say 1, square root g of sigma 1 times v1 of sigma 1 and m such. Okay, where this v is some local operator, and we'll discuss a little more about what these local operators can be as we go on. Is this clear? Okay, so this is the thing that we started out wanting to calculate. Now, of course, the problem with this path integral is that there's this huge gauge invariance. And there's a more important problem with the path integral. That is, we're doing this integral over all metrics, including the wild factor metric. But as we saw in our initial discussion with string theory, the thing that we're physically required to do is to do the integral only over only over the while factor should be treated as metrics that are different because different up to rescaling by while factor should be treated as physically identical. Okay, so this path integral will end up calculating what we actually wanted it to calculate only if the integral over the while factor is actually trivial. It's a symmetry, which is some overall factor which you can then throw out. Okay, so we're going to treat both the metric, diffeomorphisms, as well as the while freedoms as gauge symmetries. Okay, and check in the end that whatever we do doesn't depend on the while factor. Okay, we could do it a little differently, but okay, so that's what we do. Okay, so fine. So anyway, so this is what we want to do. We want to calculate the this partition, this correlation function. Now, how do we do that? This correlation function is difficult to calculate because of the gauge trick. See? So we use the usual Faddeev-Popov trick. So what's the Faddeev-Popov trick? So the Faddeev-Popov trick in this context is simply the following. It says, well, insert identity into the path integral. Now we insert identity in the following fashion. We say, well, consider the metric of your system, and let's call it G, and subtract from it the fiducial metric GTI, transformed by diffeomorphism omega, and then Y transformed. Okay, so we know. Okay, now this is one gauge fixing delta function we want to insert. There's another gauge fixing delta function we want to insert. Its product over I is equal to 1 to C delta of sigma I minus sigma I 0. That fixes the insertions of the first C operators to be at points sigma 1, sigma 2, sigma 1, 0, sigma 2, 0, and so on. Okay, so we want to put these two delta functions into a path integral. But this was the path integral we want to calculate. So we can't just put these delta functions in by hand. Okay? So what we do instead is to say, well, look at this. Look, suppose I take these two delta functions, and then I take this and integrate, and this is omega. See, the diffeomorphisms and while transformations act only on sigma I. Only diffeomorphisms act on sigma I. Diffeomorphisms change points, while transformations don't. Okay? Now, we say, well, look, what we're going to do is to insert identity into the path integral so as not to have changed the quantity we originally started out calculating. So, what we do is put an integral over omega here, an integral over 2 phi here, an integral over ti. Okay? This is an ordinary integral, ti. And then we insert this quantity, delta fp, which can depend on g and on sigma I 0. And we demand that this thing is equal to 1. So we will define delta fpg sigma I 0 by this equation. Okay? So as we saw last time, as you know, intuitively what's going on here is since there is exactly, we've been careful to make sure that there's exactly one value of these diffeomorphisms and while transformations for which all these delta functions simultaneously click. Okay? For some choice of t. Okay? Doing this integral will give us something. What it will give us will be some Jacobian associated with these delta functions, and the inverse of that Jacobian, whatever it is this delta f. Okay? Now, since the integral here is over omega, phi, and ti, whereas this thing is a function of g and sigma I 0, this thing can be taken out of the integral, of course. Okay? So, equivalently, we could say that our definition is that delta f p inverse is equal to g omega d phi d ti times these delta functions. No, G Ti is the class of diffusion. G is the real dynamical metric that enters this. Okay? Now, before we actually calculate delta Fp, let's see what we get by taking this stuff and putting it into the exponent. We add, we can write this as this times 1. And 1 is the same as this integral. So we can just enhance the path integral here to be a path integral over dg, dx mu, d omega, d phi, dθ. And with all this other stuff. Now, all this other stuff includes delta functions, which we've been very careful to choose to be linear in G. G is one of the arguments of delta. Similarly, sigma I, from this omega should be on sigma I z. It's on the fiducial coordinates, that. So similarly, this delta function here has sigma I as one of the arguments. Okay? So, in this path integral here, we had a path integral over G, and we had an integral over sigma 1 to sigma n. These two delta functions just eat up the path integral over G, and eat up the integral over d2 sigma for I is equal to 1 to c.
Sorry, so
yes.
initially you had I operator insertions, right?
We had, I think we called it M operator. No, sorry, what was it? I operator insertions. Yes. Sorry.
M was the, model.
Sorry, I said it wrong. The number of insertions was I. Thank you. I has to be greater than equal to C. So the number of insertions is I. Of these, each operator insertion comes with d2 sigma, and C of these integrals are eaten up by this delta function. Okay? And the full path integral over G is eaten up by this integral. Okay? So once we've calculated this delta Fp, whatever it is, okay, what would we have found? We would have found that the integral that we want to do is simply an integral over dx mu. When there be an integral, then we have exponential of minus s all plus log of delta Fp. Putting that in the exponent, and then we will have C. How many? C of these operate. Yeah, C of these insertions that are fixed to particular points. So then we I is equal to 1 to C square root G times some V at sigma I0, and then the remaining operator insertions continue to be integrated overall. Okay, so we'll have a product of J is equal to C plus 1 to I square root G V of sigma I0. Is this clear? Okay? Now the key point here is that this is a much simpler path integral than this guy. Because this path integral involves integration over matrix. So it's a path integral of two-dimensional quantum gravity. It's a hard thing to do as various gauges can do. This path integral, as we will see, well, at least the path that the next is just an integral over an ordinary. It's just a path integral over an ordinary conformal. Okay, now with a given metric. Okay, in S Paul, we just put in the metric. We put in the metric G omega of Ti. Yeah, the metric, and we will also continue to have an integral over the moduli. Okay, so we have to do some path integral for a particular quantum field theory with a given metric. The metric will be some G labeled by Ti. Then in the end, we have to sum over these path integrals for all metrics in our fiduciary class. We'll have to do the integral over T. We'll have to do the integral over some correlation function in some ordinary fixed metric conformal. Okay? It will be a slightly odd thing that we have to calculate. The thing that we will have to calculate is correlation functions of some operators which are given positions and other operators which are integrated with the worldsheet. And we will see as we go along, we will be able to prove that the final answer will be independent of what positions we choose to insert the operators in, which operators we choose to insert, blah, blah, blah. Alright, we'll check on that explicitly. Okay, so once we got to this stage, all that remains is for us is to compute delta fp, or even better, let's look at it. Okay, is this clear? Any questions or comments before we turn to the computation of delta fp? Okay, so now let's go ahead and compute delta fp. So, let me clear everything. Okay, now we just write on top our definition 1 over delta fp, which is function of g and sigma and 0, is equal to dti d of omega d of phi and delta of g minus g ti omega and phi e to the power 5 and delta of sigma I 0 omega. Okay, now the first thing that we want to show is that this delta fp does not is a gauge invariant function of g and sigma is of g and sigma I. By which I mean that delta fp here, if you calculate it for one set of g and sigma I, and you calculate it for another set of g and sigma I that are related to each other by diffeomorphisms and Weyl transformations, then you get the same answer. Okay? Now the proof that we give is basically very formal because it relies on operations that are correct for finite dimensional integrals or integrals over Lie group manifolds, but may or may not be correct for this huge uncontrolled integral that we have here. So it should be taken more as motivation than proof. In the end, the attitude that a lot of people take is that the final result of this answer will be the starting point for the definition. Okay? So, but anyway, you would never have reached that result without having some reason. So let's understand, however heuristically, what the how these arguments go. So the argument says that we will require these. You see, we haven't really specified what we mean by d omega. What does it mean? What is the measure of the space of differences? We haven't specified what we mean by these delta functions very precisely. Okay? But what we will require is that the measure over the space of diffeomorphisms has a property that it is left and right invariant. That is invariant under, if you take one diffeomorphism and compound it by, you take diffeomorphism and compound it by a fixed diffeomorphism. So that's a variable change. And then the Jacobian of this variable change is identity. Okay? So what's the equivalent of this for? Okay, what's the equivalent of this for a fixed group, for a Lie group? For a Lie group, suppose you were doing an integral over all group elements, for instance, all unitary, all unitary matrices. Okay? It's possible, it's always possible for a Lie group to define what's called the Haar measure, which is an integral over the group manifold. Okay? With a measure such that if you take u prime and say that u prime is u times u naught, then d of u prime is equal to d. Okay. For the u1 group, the integral over a circle, that this Haar measure is simply the usual measure over the circle, d theta. And the action of the group is translation. D theta is a translation invariant measure. It's always possible for a Lie group to find that measure. No doubt it was done by Mr. Haar, which is why it's called the Haar measure. Okay? So we'll assume that in these much bigger groups of symmetry transformations, there exists such a measure. Okay? And we'll assume that this delta function, that there exists a delta function that respects the symmetry, by which I mean if you have delta function, delta of A minus B, and you symmetry transform both A and B by some fixed element, okay, then the delta function is invariant under this operation. Again, the analogy to keep in mind for the U1 group is delta of x minus y is the same thing as delta of x plus A minus delta of minus y plus A. Okay, again for Lie groups it's possible to define such a delta function always. We'll assume that it's possible to do it for these things and to move on. Okay, now once we have these two statements, the gauge invariance of delta FP is obvious. It's obvious because suppose we wanted to calculate what so what do we want to check? We want to check that if we replace G is equal to G prime times omega times e to the power 2 phi, and similarly with sigma I, then we get the same answer. Okay? But you see, by the property of the delta function, if we make this replacement and then took out this overall constant diffeomorphism from both entries in the delta function, the delta function is unchanged. So let's do that. What that ends up doing is taking this quantity and multiplying by inverse diffeomorphism and an inverse y transformation. But then we use the invariance of the measure to change dummy variables in the integral over all diffeomorphisms to absorb that inverse diffeomorphism and inverse y transformation into an integral over a redefined diffeomorphism or redefined y transformation. So the end product of those two operations is the definition for the Faddeev-Popov determinant of G prime. Is this clear? Is this clear, everyone? Okay? So we demonstrated using this formal requirement of a measure delta function that this Faddeev-Popov determinant is invariant, is gauge invariant. Okay, right. So how is gauge invariant so hard? Because it's gauge invariant, we can compute it at any particularly useful point of the gauge orbit. Now, what's a useful point? Well, we know that there is a gauge transformation that sets G to be this fiducial metric for some value of T, which is, let's call that Ti, Ti naught, and sets this sigma I to be sigma I naught. Okay? So there exists some omega naught to phi naught. It sets G and sigma I to be equal to G of Ti naught and sigma I. Okay? So we will compute 1 over delta xc of G of Ti naught and sigma. Because that's the same thing that we wanted to compute before. Because these two are related by gauge transformations, we've demonstrated that delta xp is gauge impedance. Is this clear?
Sorry, going back to the previous argument of this delta FPV gradient.
Yes.
So, you said that when we were, let's say, transforming G to something like G omega e to the power I5, and then try to absorb it back into the hard measure.
Wait. So there are two steps. First, suppose G was equal to G prime. Let's forget the phi, just for conversational simplicity. Let's say G was equal to G prime times gauge transform by some gauge transformation omega. Okay, let's not call it omega because omega is this dummy variable. Yeah, so let's call it omega delta. Okay, then first we use the property of the delta function. That delta of we use the delta of A omega minus B omega is equal to delta of A minus B. Okay? So, what we do is take this omega, So, how do we do this? So, what we have here is delta of G omega minus G Ti, and we decided to call it prime, twiddle or whatever, omega. I'm just systematically ignoring the phi's. Makes no difference. Okay, this is what we this is what we have. Now we'll take this omega, okay, and write it as omega is equal to omega prime, okay, times omega t. This we can always do because it's a group. We multiply by omega t inverse. Okay, so then what is this? This is the delta function of G prime omega twiddle minus G Ti omega prime omega twiddle. Okay, now by the property of the delta functions, we cancel off this. But now you might say, well, up here, what we have is the integral over the omega. What we have here is omega prime. But that doesn't matter because the Jacobian for variable transformation between omega and omega prime is 1. So you change the integral variable of integral to omega prime. And now this is now the definition of the Pauli-Popov determinant for the metric G prime.
And that this is possible to do is it's an assumption that
it is an assumption. Once again, if we were doing this for just finite Lie groups, the integral over all matrices belonging to a group, then in such cases it's not an assumption. You can prove these things. But when you're doing these things, let's just say for all of these complicated path integrals, it's an assumption. Certainly mathematicians won't believe that we have proved this. But it's an assumption. Okay. Other questions, comments? Fine. So we decided to calculate 1 over delta FP of the metric in the class of special metrics that our metric is gauge equivalent to, and the points at which we want to fix our special insertion points. Because by construction, we know that it's always possible to use a gauge transformation to put the metric into this class and to put the points in these points. So we calculate it at those points. It doesn't matter. Is this clear? Now, let's do the calculation. Okay. So, you see, what we want to do is to do this integral to find 1 over delta. So, this is equal to dti, d omega, d phi, delta of G of T naught minus G of Ti omega e to the power phi, and then another delta of sigma I naught minus sigma I naught. Okay? Now we use one more assumption. Again, it's also true for these integrals over finite groups. About the nature of the measure of this path integral. You see, we can't do this calculation unless we know something about what we mean about the integral measure. Because delta f is described by an integral, but if you don't say anything about the integral measure, you don't know what it is. Okay? But now we use, an assumption whose analog again for integration over groups is true. That is, if in the neighborhood of identity, the Haar measure with no nonlinear factor reduces simply to an integral over the basis elements of the Lie algebra. Understand what I mean? Suppose you take, let's say you have SU2, and you take the group element be phi, theta, A, T. Let the other three elements basically. Okay? In a small region around identity, this measure is simply d3 theta. Okay, so this is, we don't care about proportionality factors. We just want to make sure that it's not d3 theta times theta squared or something, right? Okay, but this is true of groups, and we assume that the analogous statement is true of the path integrals below. You'll see how we use that assumption.
This is true because you're just expanding this and writing it as identity plus something.
Yes, but of course it uses the property of what du was.
How is that?
You see, what we're doing is taking the Haar measure and expanding it in a node.
Right.
So if this measure was something very odd, then this could go great. Actually, but it's almost guaranteed to be true for the following. Okay, it's guaranteed to be true for the following reason. That in the Lie algebra, in an infinitesimal neighborhood, group multiplication is simply translation. You have to go to next order to see the difference between these two. So, a group invariant measure is a translational invariant measure in the Lie algebra. And there's only one translational invariant right? This is d theta. Okay, so if you by our first assumptions, this is not a new assumption. Okay? So, now what? So, you see, in order to calculate this determinant, delta f, which is some Jacobian, we only need to know what the integral looks like to first order in the neighborhood of where the delta function clicks. Because it's a Jacobian of first derivatives. Okay? So we only have to get the measure right to first order in the neighborhood of identity. Because we've tuned things so that the clicking of the delta function happens at identity. At no diffeomorphism, no Y transformation. That's where this thing clicks. So we only need to know what the measure looks like in the neighborhood of identity. Okay? So the analog of this statement is that we have to do the integral over the natural measure in the Lie group. In the Lie algebra. Okay? What's the Lie algebra of diffeomorphisms? Diffeomorphisms are generated by killing vectors. So you just do the path integral over killing vectors. Okay, what's the Lie algebra for conformal transformation for some function? It's phi. That's simple. Okay? So, the next important step is that for the purpose of this calculation, we can take this d omega and d phi and replace it by an integral over vector fields. This one by an integral over vector fields, and this is just an integral over phi. Okay? So this becomes d2v alpha. This set of all vector fields generates a set of all diffeomorphisms, and this becomes dv alpha, and this is still d phi, and we still have dθ. Okay, great. So that's for the measure. Then the next step. What about the delta functions? But now we can be less abstract because we know how infinitesimal diffeomorphisms act on a metric. And we know how infinitesimal conformal transformations act on a metric. Okay? So what goes into the argument of this delta function? Well, there's the path which you get when things get identity, so that just cancels this. So what changes is you have delta of the change in the metric because of an infinitesimal diffeomorphism, which is del alpha v beta plus del beta v alpha. the Lie derivative of that vector field. Okay, plus 2 phi times J. G what? G T naught. Okay? Now, of course, there was also the fact that this T itself, there is an integral over T. So this clicks at Ti equals T naught. So we should add plus del G alpha beta by del Ti times delta. Okay? And so now we have correctly obtained what the argument of this delta function is in the neighborhood of in omega finite T space around the key. Is this clear? Okay, what about the second delta? The second delta function was this guy. So once again we know how a diffeomorphism acts on a coordinate. Its action is the vector field that generates the diffeomorphism. Okay? So when omega's identity is cancels that, the remaining thing is simply V alpha of sigma I naught product I naught. Okay, you see there were many sort of hand-wavy steps in getting from what we wanted to here. But once we got this, now we got it. Because now we've got a formula where every term on the right hand side, every term makes explicit sense. So now we can calculate. Okay, so let's do the calculation. So, actually, it's not like what we're after is some explicit. What we want to do is take this answer, process it, put it into a form that is useful for doing calculations later on in string theory. So the form that we put it in is the following. The first thing we'll do is to use the famous identity from delta function that tells you that delta of x is integral over k to the pi kx up to 2 pi's that are of absolutely no relevance at the level of which we're doing this calculation, dropping all constant factors. Okay? So, what we've got here is a delta function in the space of matrix. Okay? So, we use this identity twice. Once here and once here. So, okay, let's clean this out. So, the first place we use this identity is we have 1 over delta xp is equal to, now we have many integrals, like integral of v alpha, d phi, dti, and then we have, let's call it b alpha beta. This will be the Lagrange multiplier for this delta function. And then we'll have d, and let's call it something else, r, let's call it r. Okay? ri. Okay? ri alpha at sigma naught. The Lagrange multiplies for this delta function. And this I runs I is equal to 1 to c. And then we have exponential of I times Lagrange multiplier times this stuff. So b alpha beta times this stuff. So whatever it is in this delta function. Plus I times ri alpha times this stuff. So v alpha of sigma naught. Let's not call this function. It's just some discrete. everything. All I've done is take this equation and rewrite it with an integral expression for the delta functions. Okay. Now, there's actually one more thing that we have to be careful about here. You know, we want everything in the game to be diffeomorphically invariant. So when I write this, there's of course an integral here, and I'll put a square root g. So that my integration variable b now transforms like an ordinary case. So it's like a diffeomorphically invariant delta function. Okay? If we were able to carefully define our delta functions and so on, this would automatically come out because everything we're taking trouble to get data. Okay, great. So now clear this line. Now we're very long. You see, at this point, let's do some of these integrals. Let's do those with the integrals. Well, I actually just want to do one of the integrals that will make life simple. The integral that I want to do is the integral over phi. You see, phi couples very simply. It just multiplies this b alpha beta by g alpha beta, and you do the integral over phi. So what does phi couple to? Phi couples to the trace of b alpha. And the integral over phi, the Lagrange multiplier phi, sets the trace of gives you a delta function that tells you that the trace of b alpha beta is 0. Is this clear? Okay? So we can drop the integral over phi, provided we take care to ensure that we only do path integral over traceless b alpha. Okay? So that's our next step. So 1 over delta fb is equal to integral over dv alpha, node dpi, dri, okay? And then exponential of, now let's write everything out explicitly, exponential of I times integral square root g b alpha beta. Since b is traceless, we don't have to worry about this g alpha beta term, times del alpha b beta plus del beta b alpha plus I times this term r alpha bi of sigma I naught, and db, where the path integral over b here is now only over traceless, only over traceless. Is this clear? Okay. So now move to the next step. This is a beautiful integral expression for 1 over delta f. However, the thing that we want to insert into the path integral is not 1 over delta f, but delta f. Okay? However, this path integral expression is simply a quadratic integral. An integral that's quadratic in its arguments. We know that an integral that's quadratic in its arguments is simply an inverse determinant. Now, if we want the formula for the determinant rather than the inverse determinant, okay, if we want a formula for the determinant rather than the inverse determinant, all we have to do is to write down the same path integral, but just make sure that every field in the path integral commutes, anti-commutes instead of commutes. Okay? we have the formula delta fp. Now 1 over delta fp is the same thing, provided all variables are taken to be anti-commuting. So I just rewrite the names of the variables to make them more standard. Actually, B is already. So I'll just dC alpha, dTi, dRi, dB alpha beta times this exponential e to the power I square root GP alpha beta del alpha C beta plus del beta C alpha plus R alpha V C alpha Z I naught, where every field in the path variable now is anti-commuting right now. Okay? So,
sorry.
actually, sorry. So, the part that's the determinant, I should have said this more clearly. This sorry, go on.
There was one term which was del G del Ti, right? Del G alpha.
Thank you. So we should have had that. Good. So that was in this thing. So we have, thank you, that's important. Plus del G alpha beta by del Ti delta Ti. And here, this integral now is an integral over d of delta Ti, which is itself replaced by an anti-commuting thing. So let's call this delta Ti and some zeta. See, because it's part of the determinant. Something quadratic in invariant. Is this clear? Thank you. That was very important. Okay, great. So now we're happy. This is what delta fp is. However, it's possible to simplify this expression even further. The first thing we do is to do the path integral over zeta I. Okay, this is very simple because R and zeta appear so simply in the path integral.
So is it true that you are converting the moduli into some continuity?
No, the moduli themselves are bosonic integrals, and when you remember the final expression, the integral that we do includes an integral over moduli.
Right.
This is just a contribution of the moduli to the Fourier-Popov determinant. It's the contribution of the measure factor.
So in the S matrix there is no integral over moduli?
There is an integral. You see, because you remember our expression that was identity had integral over moduli as well. Okay, but the delta function ate up only the integral over the metric and the integral over coordinates. But it didn't eat up the integral over the moduli.
Right. And in the S matrix we will also have an integral over the moduli, because there also we have to integrate, we have to integrate with respect to the G and from there.
So we have an integral over moduli because, remember, we replaced identity with some integral. That integral was an integral over dt, d omega, d phi. Okay? Now the d omega and d phi integrals have just come out. They're overall integrals. But the dt integrals are there. So that's the source of integral over moduli. Okay? Why was the d omega and the phi integral special? It was because the delta functions and the measure and so on was, because we proved gauge invariance. Or, you see, what we found in the end was that the path integral did not depend on omega and phi, but it does depend on this Ti. Okay, whether it depends on phi or not is some dynamic equation. It had always procedure been completely consistent? Had we been doing things correctly? Would not depend on those guys. But it does depend on. So the final integral over omega and phi is just an integral over 1. See, because we have that integral left, but those things don't enter the answer. However, Ti does enter the answer because the metric is replaced by G of Ti. Okay? So that is there.
So in other words, can you say in this one, the metric that we fix by introducing this delta function is basically the function of the Ti also. So
yes. And then we have to do the calculation in one of these fixed metrics, and in the end integrate the answer over
all such metrics,
all such
classes that you are
all metrics in brackets. Exactly. Okay. Now let's do the integral over Ri and zeta. The integral over Ri and zeta is very simple. You see, because these things are anti-commuting coordinates. So we take this exponential and we expand it. The terms that are of order, this Taylor expansion of the exponential ends at first order. Okay, so suppose we got something like e to the power ab where a and b are both anti-commuting. Okay, this is equal to 1 plus ab squared by 2 blah blah blah. So this is 0 because we take a through b up to a minus sign and then we get a squared, which is 0. Okay? And that's the form that we have here. So, this exponential can be replaced by an integral over 1, which you see is 0. Remember that the integral of a constant over an anti-commuting number is 0. Okay? Then there's the integral over r times c. The integral takes up the r, but you keep the c. Okay? Similarly here, there's the integral over zeta. Okay? The key point that I'm using here is that there are no derivatives of r or derivatives of zeta that enter the action. If there were derivatives, it becomes a difficult coupled problem. That's why I can't do the same thing here. But since there are no derivatives, you can just do the integral once and for all. Okay? So what this gives you an explicit insertion of C of alpha at sigma is 0. And this gives you an explicit insertion of whatever's left. Okay? So we have delta fp is equal to integral dc alpha d zeta I, d b alpha beta, then exponential of I times square root g b alpha beta del alpha c beta plus del beta c alpha. Then this has gone away. What we have instead is product I is equal to 1 to c alpha of sigma I naught, and product I is equal to 1 to m, the number of moduli, and I'll invent some notation. The notation will be b alpha beta del g alpha beta by del ti. So this is a notation that's often used in Kolchinsky. It denotes the inner product between two tensors of the same rank. And what it means is take this tensor, contract with this tensor, multiply with the metric and integrate over the Cauchy. Okay, that's what we have here. We have b alpha beta times this thing times by g integrated over the Cauchy. Okay. So this is great. This is our final expression for the Fabi coordinate. Okay. Remember that the integral over b is only over traceless symmetric matrices. It's symmetric because the Lagrange multiplier for metric is symmetric. Symmetric is symmetric. Okay. Now what? This looks simple. But it's even simpler than you think. It's even simpler than you think for the following reason. Let us now choose, and I assure you this is always possible in every Riemann surface. let us now choose our conformal class of metrics to be locally always flat, conformally flat. You know, a special class. Let's choose them so that G alpha beta of Pi, okay, takes the form G alpha beta of Pi takes the form e to the power 5 sigma. Then, at least in some coordinates, you know, patch-wise in a coordinate system. In the simplest case of the torus or the sphere, you'll be able to do it globally. Otherwise, you might have to do this patch-wise. Delta. Well, this phi is also better. Okay, so we're choosing our it's global issues that will determine. You might say that all of these things are equivalent to each other. Large classes of them will be equivalent to each other under Weyl transformations, but there might be global obstructions to Weyl rescaling all of them to identity, as we will discuss in detail as we look at very specific Riemann surfaces. Okay, but now at the moment we're just interested in local analysis. Okay, so locally the metric is conformally flat. In this situation, with such a choice, okay, with such a choice of metrics, this actually becomes even simpler than you might have thought. The reason for that, and it becomes simpler once you choose the index structure. Right? So what we're interested in is the integral square root G B alpha beta del alpha C beta plus del beta C alpha. Now what do we say about that? The first thing is that we are only interested in traceless B. But in this conformal coordinate system, traceless is very simple. Right? It simply means that the only non-zero components of B are the, now we'll use the Z, Z and Z, the Z and Z bar coordinates. The only non-zero components of B are BZ, Z and BZ bar Z. There's no Z, Z bar. There's no Z, Z bar component, as we've seen many times. Okay? So, let's work out what this is in coordinates. This is integral square root G B Z Z. Okay? Integral square root G B Z Z del Z C Z with some factor of 2, because these two things are the same, plus something else with Z replaced by Z. There's an overall factor of 2, which I'm not keeping track of. Is this clear? Okay, now let's work this out even more. What is del Z? Del Z is equal to GZ Z bar times del Z bar, because the metric has no Z component. Okay? Therefore, we can rewrite this as integral square root G GZ Z bar times, so let's work out only the first term. Second term will be very similar. BZZ del Z bar of CZ. Now the first thing you know is that for a conformal metric of this form, this quantity is simply identity. The inverse of the metric, the ZZ bar component of the inverse of the metric, cancels the determinant of the metric. Okay. So this thing is simply BZZ times del bar of CZ. Now what can we say about del bar of CZ? Okay. So what is del bar of CZ? Of course, this quantity is equal to del bar of CZ plus what? Well, Z bar alpha of C alpha. Well, that's where is the usual countermeasures. And now, what can we say about this concept? See, because when we lower this, this will become a z bar. This is proportional to, that thing is proportional to g z bar alpha z bar, minus sign, plus g z bar alpha plus g z bar alpha z bar. Is this clear? I lower this, that becomes a z bar, and then I'm supposed to take this, this times this metric derivative with respect to that. That's this one, plus this times this metric derivative with respect to that. That's this one, plus this times this metric minus this times this metric derivative with respect to that. That's this one. But these two are identical, so they cancel. And this is 0 because g z bars, z bar, z bar. The only non-zero component of G is the G Z bar. This is also zero.
This crystal symbol that you written down seems to be written in terms of two kind of coordinates, right?
What do you mean?
The alphas are refer to the
Alphas are either 0 or z bar. I could make the same argument for alpha equals z, alpha equals z bar. Doesn't matter. Okay, what alpha has played no role in this? Okay? And therefore the Christoffel symbol is just 0. So this thing is simply d2 sigma bzz del z bar cz. So in a locally conformally flat coordinate system, the Faddeev-Popov determinant, okay, the Faddeev-Popov determinant is incredibly simple. It's just this object. Now, you see this action, as we've seen, you see the action is independent of this phi, which in particular tells us that it's while invariant. It's while invariant provided we regard CZ and BZZ bar as while scales. Okay? If under a while transformation, this is neutral, this is neutral, we've already seen that all other factors of the while factor cancel out. So we'll take it. Okay? Now, remember that conformal transformations are special. Conformal transformations are those coordinate transformations that leave metrics in these forms unchanged. Now, conformal transformation is made up of a Weyl transformation plus a diffeomorphism. We've seen that B and C have weight 0 under Weyl transformations. Okay? Therefore, their conformal weight is given completely by their diffeomorphism weight. But the diffeomorphism weight is given by index weight. A lower z index has the same diffeomorphism weight as derivative, therefore weight 1. So this quantity, okay, is weight 2. But this quantity is weight minus 1. Okay? And now you recognize this theory. This is the BC conformal field theory at lambda equals 2. Or lambda equals whatever the value was that said the weight of B to be minus 2 and the weight of C to be 1. B to be is 2 and C to be minus 1. Right? It's the special value that we worked out, the state operator man. That was lambda equals 2, right?
B was with lambda and C was with 1 minus lambda.
Exactly. Okay, so we have weight lambda, weight 1 minus lambda, and lambda equals 2. This matches. Okay? So what's the final result? The final result is that if we choose this fiducial metric to be of this locally conformal form, then the action of the final path integral we have to do for string theory is very, very simple. Okay, so now clearing. Okay, so the final part that we have to do is and of course there's the B bar and C bar components. Exponential of I time of S Polyakov, that part S Polyakov with the fiducial metric put in, but we've chosen this to be conformally flat, so it's simple Polyakov. Okay, plus I times, then what do we get? We got B del bar C plus B del C tilde. We also have the integral of moduli, and we have B which was lower. Okay, so sorry, how does that go? We had BZ ZZ del G ZZ I and B Z bar Z bar plus let me write that out with us. It was this square root G times this. Okay, this state product over I, where we should, where BZZ is the same thing as B tilde. Yeah, because it's BZ bar Z bar though. So it's B tilde. So this is, and by this it's the same thing as it's BZZ. Everything wrong. Okay, it was so crucial that, you know, to get this nice simple form, it was crucial that we took B to have lower indices and C to have upper indices. Nothing good would have happened if we, because in the end we got the same answer, but after I field redeterminations. You see, or covariant derivatives wouldn't have become ordinary derivatives had C had a lower index. The whole thing wouldn't have been while invariant by itself had the other. So everything would have got messed up. So this is a really convenient choice there. So you must remember B has lower indices and C has higher indices. Okay, and then there is the product I is equal to 1 to C of sigma I naught times the insertion of the vertex operators, square root G times V of sigma I naught, Vi, and then there are the remaining vertex operators. J is equal to 1 to I minus C integral of d2 sigma square root G J. Or maybe C plus J. Please.
This del G Z bar del T item. This was there. This came from Polygon here, right?
Yes.
Delta.
Yes.
Now there, if you remember, we converted this integral of t's into x's and then did the integration.
Right.
Oh. Now, what I am a little bit confused about is this was multiplied by one psi, and therefore, since you did the integration, you got the coefficient as this.
Each of it, right?
Yeah. So, why can't, these g's are in general functions of t, right?
Right. Then
derivative of this with respect to ti's will give you in general some function of ti, right?
Right.
And when you are replacing those ti in that definition by x's, then you should replace all those into x's, right?
No. You see, the thing that got converted into the integral over xi was the integral over delta t.
Oh, yeah.
Remember, it's just we're linearizing to solve for the Jacobian of a delta function. Is this clear? Okay. Now, you see, the fact that the things that enter here are the derivative of gzz and gzz bar with respect to ti tells you that you're going to get something interesting and non-trivial here. Well, you can get a non-zero answer only if the complex structure of metrics with different moduli are different. The coordinates that you have to choose. The coordinates that you have to choose in order for at different values of ti to put it in this nice conformal form can't be conformally related to each other. Otherwise, these things will just be zero. Can't be just complex redefinitions of each other. Then these things will be zero. So, in a way, the integral over ti's is like an integral over complex structures of our manifold. And we will see that all these things have nice physical, nice mathematical interpretations. Okay, so this is now the final answer in our final answer. One last step. It's sometimes convenient to put a minus here instead of plus I. It doesn't matter at all because quadratic integrals are determinant. You put the I, you get some extra factors in the determinant. We're throwing away constant factors. Okay, it's just another way of saying it is that we could freely redefine C to IC. When we do this for bosonic integrals, you have to worry about whether something's convergent or not. For fermionic integrals, always convergent. There's no issue. Okay, so this is the final form we work in. Okay, so this is we're at 4 o'clock, so let's. So this is our final answer. Our final answer for our final starting expression, the basic expression we will use again and again and again to metric space theorem. We'll enhance it when we deal with the superstructure. But it's a starting expression we use again and again and again for the scattering amplitude for states in string theory. Okay, so just let's look at it once more before we see. The answer has an integral over the x field. It has an integral over the BC coasts. Okay, and it has an integral over moduli. The answer also has some insertions. Some of these insertions are integrated over all of the worksheet. Others are fixed to special points. Those that are fixed to special points also have a factor of C associated with them. Okay? And you might ask, well, we integrate over moduli, but with what measure do you integrate over moduli? The answer is given by the fact that you have this insertion. As we will show, this insertion implies that the integral over t is invariant under coordinate redefinitions of the space of moduli. So you integrate over moduli with a particular measure of the space of moduli given by that thing there, and this is a completely well-defined integral. Okay, now over the next few lectures, what we're going to be doing is to study this formula in various ways. Okay, we will try to understand various consistency properties and so on. we were trying to see that it has the properties one expects of a consistent S matrix. Okay, firstly, lower order properties, like doesn't make sense under quadratic definitions. We will also check that it's invariant under an interesting symmetry of this path integral called PRST symmetry. And we will check many things about it. We will also then, in many examples, calculate it, just to get a feel for how these things go. Okay, so a lot of the next few lectures, not a lot of the next 5 or 6 lectures, will be devoted to studying this formula and various aspects of it. Okay, so it's a very important formula. It's a sort of central formula in string theory. It's a very beautiful and simple formula at the end. Okay, so we're going to start our study of this formula soon. But before that, you have a question. Okay, so now let's look at various consistency aspects. The first thing we want to do is to ask this troubling question of Weil invariance. You see, look at our logic. What we did was, we started with this number go to action, which was equivalent to the Polyakov action provided the Weil factor wasn't an additional degree of freedom. So we decided that the Polyakov action with Weil factor gauged was the system we wanted to study. Okay? Then we went ahead and implemented our procedure. But now it's time to come back and check whether our answer respects our assumptions. So our answer was that we were gauging Weil invariance. You can only gauge Weil invariance if the path integral has Weil invariance as a symmetry. Okay? So let's check. Now you might ask, how do we check now? Because we've already assumed that it was a gauge invariance and done all these manipulations, so how do we check? Well, we do it the way that we usually do in gauge theories. That is, if we've done everything right, then if we choose different ways of fixing gauge, we should get the same answer. Okay? So, we've chosen a particular way of fixing gauge, but it's a rather broad particular way. Because all we said was that we required that our metrics be conformally flat, and this gauge choice is invariant under Weil scales. You choose one metric, I choose some well-defined function over all of space, Weil will rescale my metric with respect to that, and I'll ask if the formula that you get and I get are the same. So we're asking, but what is the structure of, we've got various insertions. But apart from the insertions, what is the structure of the path integral we do? We're doing an integral, path integral over a conformal field theory on a given background metric. Okay? So we're asking, where is it true? Is it true? And if so, where is it true that the path integral of this conformal field theory over different background metrics that are related to each other by Weil scalings gives you the same answer? So somebody tell me the answer. When is that true? Is it true? If so. Is it ever true? If so. How are we going to answer this question? Well, one way to answer this question would be to make an infinitesimal Weil scaling and check that this path integral doesn't change. But what insertion in the path integral is an infinitesimal Weil scaling? What particular property? The trace of the stress tensor. We've used this before. So we're asking, this path integral is invariant under our choice of gauge if and only if every correlation function which involves at least one copy of the trace of the stress tensor vanishes. But we have a formula for trace of the stress tensor. Now operate a formula for the trace of the stress tensor in any conformal field theory. It's minus C by 12 times the curvature of the world sheet. The curvature of the world sheet is in general non-zero. So the only way this thing can be zero The only way this thing can be 0 is if C vanishes. It's either all the quantities that we're interested in calculating are 0, then curvature times that will also be 0. Okay? Or it must be true that C is 0. You see? So, none of this makes any sense. None of this makes any sense unless the conformal field theory we're dealing with has 0 center. If it didn't have 0 central charge, different ways of doing the gauge fixing would give you different answers. And that's it.
What is the total central charge? The contribution to the ghost also?
The central charge of the whole path integral. Because when we change the metric, we change it. No. Okay. So let's see. What is the central charge of the whole path? Well, we know that the central charge. Remember, everything is in Euclidean space. We know the central charge of the x fields is each one. So if we were to d space-time dimensions, we get a factor of d from the x fields. But if you remember, for the BC system, we calculated the central charge and found that an outlier equals 2, it was minus 26. So C is equal to D minus 26. So this whole procedure is consistent if and only if D is 26. Okay. You see what's going on? Basically, what we did was to treat wild rescalings as an invariant. Because an invariant is the classical theory. But wild rescalings are rarely invariants as quantum theories. Because quantum theories need a cutoff to be defined sensibly. Okay? And you rescale length scales to check the cutoff. Okay? So even though we defined the theory to be nice conformally invariant, on an arbitrary curve manifold, it's not easy for this thing to be wild. Okay? So, we could have rerun our whole procedure a little differently. What we could have done is gauge fix only diffeomorphisms. Left the integral over phi, the scale factor of the world sheet, explicit. And let the final answer in terms of an integral over phi as well. And the action for phi then would have turned out to be the value of the path integral of string theory, of this conformity theory, as a function of phi. This is something we at least discussed computing. We didn't compute in class, but I think it was one of your exercises. Do you remember I at least told you that the answer is del phi plus some. Does anyone remember this? The point was to take the equation that the change in the action, the change in the path integral, is curvature under an integral variation of phi, and then to treat that as a functional differential equation and integrate it. So it's possible to do. If you guys haven't done this, this is an exercise I want you to do. Okay? And so then what we would have got had we dealt a little differently. I'm not going to do this. Just telling you. Had we dealt a little differently, what we would have got is path integral over x and phi with a non-trivial action for phi. Had C not been, in the critical dimension. Okay? So phi would have become another physical field, like the x fields. Except that it would have been a little different from the physical fields because this, as we will see, is the way I've written this, it looks like it's got the same actions. There's also an R phi in this theory. Makes it different from the other physical fields in various ways. So we would have ended up perhaps with a consistent string theory, but not a Lorentz theory. Okay? Where we would have got more degrees of string fluctuation than we started out thinking we would have had. The fluctuations were somehow in these phi directions in addition to the transverse directions of strings. Now, that we will turn at later points in this course when we talk about compactification to theories of this sort. At this introductory point in the course, we're not interested in such complicated things. we want to study string theory propagating on direct and pairing transfers. Okay. If we want to do that, phi has to disappear as a degree field. Integral over phi is trivial, just a constant which we can just factor out. Okay, so at this first pass, that's what we are asking for. Okay, and that works only when it is. It's sort of quite, it's non-trivial that it works at all. That there's any value of d, any integer value of d for which it works. And bit d equals square root of 3. Okay, it makes no sense. It's non-trivial that it works for any integer value at all. Of course, it's a big integer value. We'll come back to that. What with the connection with the real world, we will come back to that. Okay, so that's the first thing. So this calculation gives us a second pass on the critical dimension string theory. Okay, any questions or comments on this? Okay. Okay, now right. Now the next question we're going to ask is, what about the operator insertions? You know, what operators are we allowed to insert in here such that we get sensible answers? Okay? Now the answer to this question is given by reasoning that's very similar to the answer to the question that gives us d equals 20 cents. You see, the final answer mustn't, for any legal question, cannot depend on the choice of fiduciary metric. Cannot change under wild rescalings of our gate choice in fiduciary metric. Okay, there was one place in which you could have entered in this basic bulk action. But there are other places in which you could enter, namely in the insertions. Okay? Now, what are the insertions? Okay. So the insertions here, are dz bar, okay, times square root of g, so that's e to the power of 5, times v. Okay? So now this quantity, in order for this to be a well-defined, insertion, an insertion that doesn't depend on this, the phi that goes into the fiduciary metric, it had better be that this v transforms under phi in such a way as to cancel this explicit e to the power of phi dependence of this metric. Okay? Another way, a necessary condition for this,